As promised in the last video, we've cleared the key terms for just the most absolutely essential terms. I'm going to do a very quick review of these terms right now in a Jupyter Notebook. Okay, we finished the last notebook, so it's time for a new one. So we're back in my github.com/johncrone/mlfoundations GitHub repository. And so we're now starting off with subject 6 in my Machine Learning Foundation series, Intro to Statistics. So you can click on that, or you can go into the notebooks directory, and you can find that subject 6 notebook called Statistics. When you go there, as with all of the notebooks in this Machine Learning Foundation series, all of the code has been executed here for you in GitHub. So you can scroll along and follow along statically if you'd like to. However, again, as with all of the notebooks, I do recommend following along interactively. So you should be able to click on this Open in Colab button, and that will open up the notebook in the interactive Google Colab environment. And if for some reason the left click doesn't work, you should be able to right click and open in New Tab. When you do that, you'll be in the notebook running in Google Colab. So the top of this notebook has that quick review of the most important topics. This is going to go very quickly. So the imports that we need, at least at this early stage in the notebook, NumPy, SciPy, Matplotlib, Seaborn, these are all dependencies that we've worked with before, including in the probability topics that we covered already in these live lessons. And in order to try to be able to get the exact same outputs every time I run this notebook, as well as allowing you to get the same outputs as me, we can set the NumPy random module seed to 42, the magical and best number, the answer to everything in the universe. So the key topics that we need to know, I already wrote these on the whiteboard for you. Let's run through them very quickly. If you don't know these terms very well, you should go back to those videos earlier in these live lessons to make sure you know these topics very well, because we're going to be talking about them a lot as we move now into this statistics content. All right, so measures of central tendency. These provide us with a summary statistic on the center of a given distribution. So if we have a skewed distribution like this distribution X here, then the mean of that distribution, we calculate it this way. I'm not going to go over that again. We would often call the mean X bar. I do want to note here a new way of calculating the mean that we haven't talked about earlier, which is taking the vector of values X, in this case, that makes up our distributions, and you can very conveniently just use the mean method on that vector X. And you can do that because X is a NumPy array. All right, so plotting out the mean on our distribution, here is the mean in orange. The median is another common measure of central tendency. And again, we can use NumPy, passing in our vector X into the median method to get the median of the distribution. And we talked about earlier how the median is less impacted by skew. So the more skewed our distribution is, the median might be a better measure of central tendency than the mean. But if the distribution is normally distributed, then the mean, the median, and the mode, frankly, all the major measures of central tendency would be the same value. So the mode is least impacted by skew, but it's typically only applicable to discrete distributions. So for continuous distributions with skew, like salary data, the median is typically the choice measure of central tendency. Remember that the mode is just the most frequently occurring data point, which is why it only works for discrete distributions, not continuous random variables. So here is that depiction of how the median in green is dragged less toward the tail, the long tail, like the mean is. All right, so that covers measures of central tendency. Another very big key point is measures of dispersion. And so we've got variance which here's a new way of calculating it that I hadn't shown you before. Again, because x is a NumPy array, we can just call the var method on it, and that gives us the variance, which we can denote with sigma squared. So standard deviation is the square root of sigma squared, which gives us just sigma, and so we can symbolize standard deviation that way. And so that variance that we had here, we can simply take the square root of it, and that gives us the standard deviation. The nice thing about standard deviation is that its units are on the same scale as the values in our distribution. You could also use the built-in standard deviation method, std, on a NumPy array to calculate standard deviation that way. And we get the same thing as if you take the variance and take the square root of the variance. So when we have a standard deviation, we can say plot that on a chart. And so this gives us a sense for our skewed distribution. This is its mean. And the range between these olive green lines is 2 standard deviations, because I have one plotted one standard deviation below the mean and another plotted a standard deviation above the mean. All right, and then our final important measure of variance is standard error. We're going to be talking about this a lot in these statistics topics, so definitely a good one to know. The standard error is the standard deviation divided by the square root of n, however many samples we have. So here is how we get that value from standard deviation, but you can also use existing methods like the standard error of the mean, SEM method, in the SciPy stats module. And so we can run that. We see that we get a very slightly different answer from when we did it manually. And the reason why is because of this concept of degrees of freedom, which I've been skimming over so far in these live lessons. And I've just been saying, you know, whether we have 1 degree of freedom or 0 degrees of freedom, that doesn't matter very much, because in machine learning we tend to have large data sets. And so we are going to explain what degrees of freedom means in the context of statistics shortly. But for now, it is a concept that you can largely ignore. However, if it makes you uncomfortable to be getting a slightly different answer like we do here, you can get the exact same answers here by setting your degrees of freedom equal to 0 manually instead of using the default 1 degree of freedom. So standard error, this metric here, enables us to compare whether the means of 2 different distributions differ significantly. So when we have 2 distributions and their means are not the same, are those really different? Does it mean something? Is it significant or not? This is a huge, huge focus of the intro to statistics that we're covering right now. All right, and then on to a quick refresher of the Gaussian distribution, also known as the normal distribution. So if we create one here, and then we look at it in Seaborn, there's our nice bell shape. And this normal distribution has a mean of 0 and a standard deviation of 1, meaning that it is a standard normal distribution, right? So we can also call that a Z distribution or Z distribution, depending on where you are in the world, which we can denote this way here. So we're going to be talking about Z distribution, Z scores shortly, our first new topic. So normal distributions are by far the most common distributions in stats and machine learning. They are typically the default option. That is because normal distributions assume the greatest possible uncertainty about the random variable that they represent. And we talked about that earlier already. And we also talked about how whether an underlying random process is simple or very complex, under lots of common conditions, we can assume that we would have a normally distributed set of means if we sample values from that process. And so that surprising reality, to some extent, is the central limit theorem. And so we already talked about this earlier in these live lessons, but the idea is that if we sample means from any distribution, if we have a small sample, it's not likely to necessarily look normally distributed. But as we sample more samples, we start to see that it's normally distributed. And especially as our samples get larger, we see that they become normally distributed and centered around the mean of our source distribution, right? So getting very large samples now indeed, and we get a very tight normal distribution around the mean of our source distribution. And so even if we sample from skewed distributions, we still, when we sample from it and calculate the means and then plot those means are normally distributed. So even if it's a skewed distribution, we get normal distributions as sample means from the original source distribution. That is the central limit theorem. And even if we sample from multimodal distributions, like this one here, still, we sample means from it, boom, we get a normal distribution. Even uniform distributions, you get the idea. No matter what kind of distribution, when we sample from it, we get a normal distribution. So that is the central limit theorem. And so things like the t-test that we are going to be covering shortly, if we want to compare two means, does this experimental group that receives a treatment, does it differ significantly from a control group that receives a sugar pill, a placebo? We can use this central limit theorem in that statistical method as well as tons of machine learning models to make inferences confidently. It's a very powerful theorem indeed. Nice, so that was a quick refresher of the really key concepts from the probability theory that we've already been covering in these live lessons. Got them up on the board, and we're now going to rely on these key terms to move forward and study statistics. The first concept that we're going to learn about is the Z-score.